Welcome to the lecture series on reinforcement learning. In this video, I ask, why is surprise useful? In an earlier video, we have seen this sequence of images. Let's look here and see a similar sequence appearing from left to right. Okay, that's it. So I've seen this sequence several times, but each time I see the 4 appearing, I still get a little shock. Why is that? Surprise is against expectations from our current belief, but we cannot help but making models of the environment. I do not tell you what it's about. You just see the sequence, you start to see regularities, and these regularities raise expectations that arise from your model of the world that you made spontaneously. So we always make models. We cannot help. We do it. But then the world is so complex that we know that our model cannot be perfect. And now surprise, and that's the hypothesis, surprise enables us to adapt our models, to adapt our imperfect models, to detect imperfections and improve the model. So surprise boosts plasticity. It increases the learning rate. We know that in models of machine learning, in models of reinforcement learning, there's always a learning rate parameter. And so the hypothesis is that surprise increases this parameter of learning rate. Now note that when I show you these images, sequence of images or sequence of numbers or something else, there's no reward. So it has nothing to do a priori with reward-based learning. Yet there's an interesting analogy. We have seen that dopamine encodes reward, or more precisely success, defined as TD error, reward minus expected reward. And dopamine is spread out from a nucleus deep down in the brain all over cortex, not really sensory areas, but all over cortex. Similarly, there are other neuromodulators like noradrenaline, also called norepinephrine, that is generated deep down in the brain and makes axons all over the brain. The standard view is that dopamine is related to reward minus expected reward, but it also has a small surprise or novelty component. Similarly, the standard view is that norepinephrine or noradrenaline is related to surprise and novelty, but it may also have a small reward component. So globally, we have different neuromodulators that can influence the brain in a temporally precise fashion, and therefore we can argue that similarly to dopamine that can boost plasticity based on reward, norepinephrine, noradrenaline could also increase the learning rate, but now based on surprise. So let us look again at the formalism of 3-factor rules here in the presence of an eligibility trace. We have ascending neuron J with activity xj, which has a link to a receiving neuron I. The receiving neuron I has activity phi, and if we have a co-activation of both neurons, then G of xj will be positive, F of phi will be positive, and that will increase an eligibility trace Zij. Later, this eligibility trace decays over time. However, if a modulator signal M comes, and this modulator signal can be global, reaching many neurons, a broadcast signal, if this modulator signal comes before the eligibility trace has gone back to 0, then the weight from J to I, this link will be increased, proportional to the eligibility trace and proportional to the value of this neuromodulator. And this neuromodulator M is a function of S, of the signal, and this signal could be the TD error, but it could also be surprise. And now if you look at this formalism, then eta times M together is like an effective learning rate that's modulated by the modulator, that's modulated by the TD error, or that's modulated by surprise.